Thank you. Thank you. So good afternoon, everybody. Very grateful to the organizers, Giovanni, Pierluigi, and Vincenzo, for asking me to deliver a lecture in this PhD course. Thank you all for being here, really, to listen to me. For the next couple of hours, we're gonna talk about climate analogues as the title of my presentation suggests. So a few words about the topic and this project in particular. As Pierluigi mentioned during the introduction to my work, so I mostly deal with philosophy of physics. In fact, I currently have a joint project with Vincenzo on analogical reasoning and contemporary physical theories, which is partly related to what I'm going to talk about today. But today it's not about physics, it's about climate science. And so this project puts together two distinct lines of research that I'm very interested in. One is the general issue of surrogative reasoning. So how do we reason about systems that we don't have any epistemological access to? And analogy is one of these forms of reasoning, if not the most fruitful form of surrogative reasoning. And the other line of research is climate science in particular. I'm interested in how to deal with uncertainties in physical models of the climate, and then in the designing of adaptation and mitigation strategies to cope with climate change. And so this project brings together these two main lines of research besides philosophy of physics. And it's based on joint work with these colleagues of mine, Hernan Bobadilla, Rawad, Skaf, and Francesco Nappo, all young researchers in philosophy of science that are part of my group in the Department of Mathematics of Polytechnic of Milano. So, well, enough with the introductory words. So my plan is to give the whole presentation and then open the floor to questions. But if at any point during the presentation you wish to stop me to ask for clarificatory questions, or if the pace that I'm choosing is not suitable, too slow, too fast, just, don't be afraid to jump in. Maybe write something on the chat if you want, and then Giovanni or Pierluigi will let me know. Unfortunately, I won't be able to follow the chat while giving the presentation, but they're going to assist me on this. So by all means, at any point of the presentation, feel free to interrupt me for any clarificatory question. So I plan to talk about an hour, more or less, and then we're gonna have questions about the content of the presentation. So let's start by stating the problem at stake. So it has to do with the methodology of climate analogues, so a special kind, namely spatial climate analogues, that are tools of scientific research in climate science that have been developed since the 80s, especially with the aim of dealing with the problem of adaptation to climate change. And one of the early examples of the use of spatial climate analogues is some work that has been done by Bernard Thorson and collaborators, wherein they identified the north of Ireland as a good analog, a good climate analog for the future climate of Iceland, with the purpose of understanding how the growing of grass will change due to climate change in Iceland. And so they, the work by the authors led to identify Ireland or the north of Britain as a good analog of the future of Iceland. And here's a quotation from some other authors that have done a lot of work more recently on spatial analogues, Ellegate and friends. And it is a very telling quotation that I'm going to read before raising the main questions that will entertain us during the presentation. So the authors wrote, the solution we want to explore, solution to the problem of adaptation to climate change, makes a heuristic use of climate analogues to circumvent the absence of credible counterfactuals and fully fledged visions of adaptation mechanisms. To do so, it is possible to use information provided by a CTB currently experiences in climatic conditions that can be considered as reasonable current analogues of the projected, the future climate conditions for another city A. So city A here will serve as the target location. City B is the source location that is allegedly the climate analog of CTA. So there are at least two outstanding issues that we're going to discuss today. So what does it take for for some location to be a good analog of the target location? And after such a good analog is identified, can it drive inferences that we can consider as plausible enough about the future of the target location? And we're gonna try to answer these questions throughout the presentation. And here's the plan of the talk. I will start out by introducing the methodology of spatial analogues, explaining how they rest upon a few assumptions, and in particular on the use of topological metrics of dissimilarity that are meant to establish how dissimilar the target and the potential analogues are. And then we're going to start addressing the first question about when exactly or what it takes exactly for a location to be a good analog of another one. In particular, most of the literature on spatial analogues is engaged in the attempt to find the best climate analog for a given city. And that raises two problems, which I call problems of non-uniqueness. The first is an issue of non-uniqueness or the underdetermination of the source location. But there is also a second problem on non-uniqueness, which is that of non-uniqueness of the target. And we will see exactly how they arise. And then after raising these problems and suggesting some possible solutions to them, we're going to address the other main issue about the plausibility of analogical inferences. And we will contrast the methodology of spatial analogues with the use of standard techniques for analogical reasoning. And in doing so, we will raise other three problems that are interrelated. The main one is the problem of average. And then there are the problems of non-causal correlations and the problem of inferred properties. And the second part of the presentation, we will address the question that is in the title, the presentation, namely what are climate analogues good for? In light of these 5 problems, there arise doubts about the usefulness of the reliability of climate analogues, and we will claim that they can fruitfully be put in place in applications in impact, adaptation, and vulnerability AAV studies of climate change. And we're going to make 2 main recommendations in this respect. Namely that one should actually evaluate an whole set of plausible climate analogues rather than searching for the best climate analog according to a given dissimilarity metric. And then that this set of plausible climate analogues should be further restrained or restricted by resorting to local knowledge of the target and the source. The methodology of spatial analogues. Let's start by pointing out that the IPCC third assessment report already in 2001 distinguished between 2 main types of climate analogues, spatial and temporal analogues. Spatial analogues aim to find some source location whose present climate is most similar to the projected future climate of the target location. Whereas temporal analogues aim to reconstruct the remote past of the target location so as to project, based on what we can reconstruct from the past, to project its future climate under a variety of different scenarios. Now, clearly, temporal analogues rely on paleoclimatic data like fossils, and these data are very indirect and are often scarce. Although some recent work in the literature that by Wilson that I recommend you to read tries to assuage these worries of the indirectness of paleoclimatic data. But spatial analogues at least don't suffer from these limitations because they avail themselves of a large amount of data about the present climate. And so these data are direct data. And as such, they seem to be much more promising than temporal analogues in order to extract useful information about the impact of climate change. And so that's the reason why we decide to focus on spatial rather than temporal analogues. Now, a few caveats that we need to keep in mind when applying this methodology that I'm going to sketch. First of all, the data, climatic data, are very seldom about about an exact locations. Rather, they're typically distributed over extended regions. So the standard technique to deal with this fact is to partition the region under the geographical area under study in a large number of grids of equal size. And then exact locations like cities will be associated with the grid that is center. Each city will be associated with the grid which is centered on these regions. Another issue concerns the relevant climatic indicators. Typically, temperature and precipitations are taken to be the standard ones. But as a matter of fact, even other properties can be relevant to understand, to assess climate change, depending on the purpose at stake. Whether it is agriculture in rural areas, for instance, or flooding in the cities. The data are also collected through measurements that are made over time. These measurements are done at very regular intervals of time, the scale of months usually, and for a sufficiently long period, typically 30 years. Lastly, let me point out that there is also a kind of temporal asymmetry between the target and the source, because direct observations, so the collection of data, is done for the present climate of the source location, whereas the data that are supposed to be about the future climate of the target are just projected values of the climatic indicators. Okay, so these temporal asymmetries must be kept in mind when assessing the worth of the spatial analog methodology. Now, let's get a bit more formal. The climate of a given location can be captured mathematically by an n-points vector distribution, where each point corresponds to the measurement of the relevant indicators, and the number of points corresponds to the number of measurements, namely the number of years or months at which measurements are made. So psi t will refer to the vector distribution of characterizing the climate of the target location. It comprises n values for some measured quantity x, whereas the psi s is the climate distribution for the source. It's also made up of n points, psi n to psi, sorry, yn to y1 to yn, where y is another measured quantity. Okay. Let's say that the dimension, namely the number of relative indication, is d. It's typically the number of three indicators are sufficient normally to characterize the climate. So both x and y belong to the space R to the n. So each of the relevant indicators, which are in a number d, will take real values, of course, because we're measuring real quantities. That's why x and y belong to R to the n. Now, how do we compare psi t and psi s in order to determine whether the target and source have similar climate? Well, we do that by introducing a dissimilarity metric, so a topological or geometrical notion, a measure of dissimilarity. Let's say this psi t, psi s will capture the value of the chosen dissimilarity metric. And clearly, the lower the value of this function, and the more similar the two vector distributions are supposed to be. And on that basis, of course, the best analog will be the candidate source location having the lowest dissimilarity value when compared with the target location. Okay? And so most of the literature on spatial analogs aims at finding the best analog for a given location. Here's an example, a completely made up example, just to illustrate how this methodology works. It has to do with the future of Venice. Here you see Venice in the 2020s, okay, the San Marco Square. And the climate of Venice will be projected in the future, say 30 years. And so here we have a picture of Venice in 2050 with a lot of flooding. well, actually, the picture is more recent because we know that Venice undergoes a lot of flooding regularly, but it is very illustrative of what could be a standard state of the future of Venice. Hopefully not, but it could be. And then once we identify the projected future climate of Venice, then we can find or try to find another city that in the present has a similar climate to the future climate of Venice. And we do that by means of a climatic dissimilarity metric, okay? And this metric will enable us to rank other locations from the most similar here at the bottom to the most similar here at the top. Okay, now it is a very, very, very a completely made up example, you know. So let's suppose we take a very pessimistic projection, okay, with a lot of increase of entropy or increase of temperature in the future. And so if we look at, say, 4 locations, we can probably rank them according to our climate dissimilarity metric in the following way. So Strasbourg, which is also known as the Venice of the North, okay, already has a colder climate than Venice. So according to these very pessimistic projections that we're making, just as a toy example, Strasbourg will be probably the worst analog in terms of climate. Valparaiso, a city in Chile, it's also a sea or an ocean city, I should say, with a large port. Tends to be already a bit hotter nowadays than what Venice is, so, but it's certainly warmer than Strasbourg, so it's probably gonna be the second worst analog in the bunch that we have. Yeah, Suzhou, the Venice of the East, or one of the many Venices of the East, is a city in China, has a very, very, very hot weather already. So it's likely to be the second best analog. And the best analog, at least in the list, is likely to be Las Vegas, where you can see here, you know, in the picture, the part of Las Vegas which is called the Little Venice, which is like, you know, a fictional representation of Venice with a canal and the San Marco company there. Okay, now Las Vegas has a very desertic climate, so with a very pessimistic projection for the future temperature of Venice, Las Vegas and Little Venice in particular is probably the best candidate for, or the main candidate for best analog in this list. Okay, so but I hope at least that I could, with this picture, illustrate how to the technicalities, how the methodology works. Okay, so first we project the present the climate of the target location from present to future. Then by means of the dissimilarity metric that we choose, we compare the future climate of the target with the present climate of a list of candidate sources. And then the one with the lowest value, in this case Las Vegas, will be the best analog. And the hope is, of course, we can learn something from the best analog that can be applied in the future to deal with the future climate change of the target. Okay. Now, does this methodology work? Well, as I mentioned at the beginning, there are a number of problems, and so let's see them in detail. First of all, let us notice that there exists a lot of different well-defined measures of dissimilarity that are employed in the literature of spatial analogues. And so it's worth to look at two of them, the standardized Euclidean distance and the nearest neighbor distance. And we started by looking at the first one, but in the specific case of the distance between points. I spent some time explaining the meaning of this formula. And then I was about to say that once we define this distance between points, for each point in each on the two distributions, we can find the closest neighbor, namely another point which minimizes the distance set between the reference point and itself. And you can do that, of course, for points in the target distribution and points in the source distribution. And then you can count, and that's going to be the number n, the quantity of points whose nearest neighbor is in the same original distributions. That is to say, if we're looking at a point in the source distribution, then the nearest neighbor should belong to the nearest distribution, to psi s again. And likewise, if we originally belong, the reference point belongs to psi t, and its nearest neighbor also belong to psi t, then all these points contribute to the number n. Okay, if they do not, if the nearest neighbor does not belong to the same distribution of the reference point, that it does not, then it does not contribute to the number n. And then the metric, which goes under the name of nearest neighbor distance, is here symbolized by d and n, which is the ratio between the number n of points whose nearest neighbor is in the same distribution over 2n, which is the overall number of points, because each distribution has n points. Okay. And so low values of the nearest neighbor distance will tell us how distant or mutually dissimilar target and distributions are. Okay, because a low value of this guy means that n is very small, and so the points in the distribution don't belong. So and so there are a lot of points in one distribution whose nearest neighbors don't belong to the other distribution. Now, good as it might be as a dissimilarity metric, this measure turns out to be discrete. Okay, it ranges from 0 to 1. There are actually two n+1 values that come out at intervals of 1 over 2n, but it is discrete. And so it fails to comply with a desideratum, a criterion called continuous discrimination, whereby we should be able to rank in an ambiguous way all the candidate sources. Okay, but for this unambiguous rank or continuous discrimination, you need a continuous metric, and d and n is not continuous. So the standard Euclidean distance between averages distributions, which is different than the distance between points, provides a solution to this problem of the previous metric. Then this distance is defined in this way. Okay, so you take the average of all endpoints in the distribution, the target distribution, minus the average of the source distributions. You normalize it by, remember, here we have a product of the standard deviations. Here you just normalize it with the standard deviation of the target. Then you take the square of this and you sum over each indicator, and again take the square root because it is a standard Euclidean distance. And what this formula gives us is a way to quantify how much the two distributions are dissimilar on average. And because it grows continuously from 0 on, as the averages between the two distributions become more distant from each other for each indicator, this metric certainly fares well with the criterion of continuous distribution. However, notice, as I pointed out before, the year standardization is relative only to the target distribution and not the product of target and source. And so this measure turns out to be non-symmetrical. In fact, if you compute it with respect to psi t and psi s first, you're going to get, in general, a different result than computing it with respect to psi s and psi t in the order. Okay. So what this means is that even if the source might be maximally similar to the target, the reverse is not true. So S might be the best analog of the target, but not vice versa. Okay. Now, what do we learn from just these two examples of the similarity metrics? Well, that metrics behave in a different way. Actually, if you look even at the other examples of metrics, you see that they all have some virtue, but also defects. But the most important thing, at least for our purposes here, is that they provide inequivalent outcomes. So in their review, Grenier and others show that if you consider the future climate of Montreal, you projected for the years 4170, that 3 decades, under the model called SIM01, then most of the locations that are in the range of 250 in terms of being ranked as analogues will be found in Nova Scotia, according to the standardized Euclidean metric between averages. But that is not the case according to the other metric, the nearest neighbor distance, as well as the other measures of dissimilarity. Okay, so different measures of dissimilarities yield inequivalent results. And that leads us to the problem of non-uniqueness of the source, because if two metrics identify different candidate sources as the best analog, then even for the same target, then we're gonna have multiple candidates for best analogs. Okay, so there's a problem of non-uniqueness, of underdetermination of the best analog, which depends on the arbitrary choice of the dissimilarity metric to adopt. There's also another problem of non-uniqueness, as I anticipated before. It is the non-uniqueness of the target. So not only the source is underdetermined, but also the target. In fact, recall that while the points of psi s are informed by direct, actual observational data, the points of the target distributions are just expected outcomes that come from model simulations. So given that there are different models, climate models that we can adopt, and we can choose different radiative forcing levels, there will be also a plurality of projections of the future climate of the target, thereby giving rise to the problem of non-uniqueness of the target. And mostly there are 3 sources of underdetermination of the target, and that is true even if we decide to settle on a given metric. So the problem on non-uniqueness of the target doesn't depend on the choice of the metric. Instead, it depends on the fact that we do have different scenarios under which we project the present state of the climate. There is a variety of circulation models that dictate the time evolution of the climate. And also there are different layers of uncertainty throughout the whole computational process that lead to the projected climate. So let's zoom into these three sources of underdetermination of the target in the next 3 slides. The first is the fact that climate, so first of all, recall the climate projections are meant to give predictions of the future climate that are conditional on a certain radiative forcing, okay? Conditional on a certain emission scenarios, okay? The quantity of CO2 that we decide to keep, to throw in the atmosphere. Now, the problem is that, or what seems to be a problem is that there is a plurality of such scenarios that are used by climate scientists, and there is no a priori preference over any for any of these scenarios. There are 2 main classes of emission scenarios: the so-called representative concentration pathways, RCPs, that refer to the different levels of radiating forces that we can use 2.6 watts over square meters for the year 2100, or 4.5, or 6, or 8.5. Okay, so for any of these radiating forcing, you're gonna get a different projected climate. The most recent generation of emission scenarios instead is called shared socio-economic pathways, SSPs. So while the old generation of scenarios, RCPs, only use physical constraints, radiating forcing, SSPs instead take into account socio-economic or socio-political and institutional factors. And there are 5 main of such scenarios. One in which the future world is sustainable in terms of the organization of society. Then there's a middle of the road scenario, a scenario in which there are regional rivalries, and another in which we have very pronounced inequalities. And then the last one, in which there is a very rapid growth of the population and the energy demand. Again, under each of these scenarios, you're gonna get a special a specific projected climate for the target. And so, depending on what scenario we use, we're gonna have a different target. But that is also true depending on what climate model we choose, okay? In fact, there are several different global circulation models that even if we fix a certain forcing level, they will give different results for the target, and thereby will lead us to identify different distinct analogues for the target. As an example, let's look again at Hellegate, that showed that if we look at Paris as the target location, its future climate in 30 years, it will be most similar to Bordeaux, according to the Arpège model. But according to this other model, had RM3H, the best analog will be Cordoba rather than Bordeaux. Okay, now, of course, we can apply robustness analysis as it is standardly done by climate scientists, but there we add a statistical dimension to the search for the climate, for the target, the future climate of the location of interest. And even if we do so, there still remains the third source of underdetermination of the target, which is the fact that we have projection uncertainty of various kinds. We have uncertainty about the initial conditions, so there's a lack of knowledge about what is the what is exactly the present state of the climate from which we should launch our model simulations, computer simulation. There is also structural uncertainty about the modeling equations for the evolution of the climate, parametric uncertainty about the numerical values that the salient parameter of the model should be tuned on. There's also uncertainty about the fact that we don't know how to translate the results of our climate models, which are on a global scale, to local scales. Okay, and of course we want to know the local climate of the target and the source. And lastly, we have a kind of non-physical uncertainty or uncertainty about non-physical factors, especially socio-economic factors that are crucial over and above the change of climate to determine its different impacts in different cities. If the cities are socioeconomically different, then even the same type of climate change will affect them differently. Okay, so now we have problems with the identification of the best climate analog because both the source and the target are underdetermined. Now let's suppose that we can choose a dissimilarity metric and fix a preferred scenario and a preferred model, and we find our best analog for the target location. The next question, which is philosophically perhaps the most interesting one, is what can we infer about the target from the best analog? Can we draw any plausible inference about the future of the target city from its twin city? And so that's the question we're going to look at in the next part of the talk. To understand, so actually to have a grasp on how to answer to this question, let's contrast the methodology spatial analogues that we just sketched with standard analogical reasoning. In standard analogical reasoning, whatever it is, because of course there are very many approaches to analogical reasoning, but this is more or less the standard scheme. Okay. In the standard scheme, we compare target and source. We look at the properties of the target, say properties to P1 to PD, and we check for similarities between the properties of the target and the corresponding properties of the source, the P stars. So we establish some one-to-one correspondence between each of these properties. And if there are a number D of similar properties, then the analogical inference will suggest that if the source possesses a P star, a P D plus 1, an additional property, then also the target should have that property, or the corresponding one at least. Okay, so from this bunch of similarities and the fact that the source has an additional property, we infer also that the target should have the corresponding additional property. That's analogical inference. Of course, this is non-deductive reasoning, so we have no expectation that there's any strict derivation of this conclusion. The conclusion is subject to uncertainty, like on all non-deductive schemes of reasoning. But it could be plausible nonetheless, under certain conditions, and the whole discussion in the literature is about the nature of such conditions of plausibility, if any. Okay. Now, of course, beside the positive analogies, so the similar properties between target and source, there are also what we call negative analogies, so properties that are not similar, and the neutral analogies, so properties for which at the present stage, we do not know whether there are similarities or dissimilarities between T and S. Two questions then arise. Are positive analogies, especially if we have a large number of these positive analogies, sufficient? Do they provide a sufficient basis to draw analogical inferences about the additional property? And how does the strength of such an inference be affected by the presence of negative or even neutral analogies? Okay, and so the debate in the literature is pretty much about these main issues, and there are competing accounts. Let me just mention a venerable account, which is the one by Mary Essay, 1963. And she claimed that similarities between target and source, in order to make a plausible inference, they must hold in relevant respects, so they must be about relevant properties, and possibly there should be a causal connection between these relevant properties that drive the conclusion. Now, it's tempting to see SS proposal or some other proposals along these lines as very intuitive. Be that as it might, there are differences with the methodology of spatial analogues that complicate the picture. In particular, spatial analogues do not hinge upon the one-to-one correspondence structure of standard analogical reasoning. That's again the picture I showed you before. Now contrast it to the picture of the methodology of spatial analogues. Here it is. You don't have one-to-one similarities. You do have an average across the relevant climatic indicators. You take the average for the target, the average for the source, depending on which metric you adopt, then you determine how similar they are. And then you have a question mark about the additional property to be inferred. Okay, the methodology of spatial analogues just look for the best analog, but doesn't say what we can infer about the target. It just tells us from a climatic point of view, this city is the twin city of another, of your city of interest, or the target city. What can you learn about this best analog? That's very often left as unspecified. Okay, so here's the main differences between standard analogical reasoning and the methodology of spatial analogues: the number of indicators. Usually, the larger the number of one-to-one similarities, the more reliable the inference might be. Whereas for the case of spatial analogues, you just look at a very restricted number of indicators. 3 will be typically enough to characterize the climate. Temperature and precipitations, for instance, plus another one depending on the purposes. The standard scheme rests upon the one-to-one similarity structure, whereas the methodology of spatial analogues only offer statistical averages among the relevant indicators. And lastly, as I pointed out, in the standard scheme, we know how the inferential step works. In the case of the spatial analog, we don't, yet at least. So there's some work to do in order to specify how we can draw an analogical inference that can be plausible. from the best analog. But here we face three main problems. Okay, now, first of all, the condition of low dissimilarity value is not a sufficient driver for analogy. Okay, it doesn't necessarily imply that the candidate source location is a good climatic analog of the target, because there's a problem that we call the problem of average. By averaging over a small set of indicators, okay, the result that we obtain from the application of a measure of dissimilarity is insensitive to some potentially critical difference between the target and the source. Some indicators might be very different, but they're just counterbalanced by the others being very close. Okay, and it is potentially dangerous. Why? Well, consider another example, the one by Koff and friends, that look for the best analogues of 12 European cities. And they use aridity, heating degree days, and cooling degree days as the three main indicators. Now, if you average over them, the result that you might obtain, and in fact the results that Koff and friends obtain, could be such that you overlook some levels of aridity in the target city that maybe can go beyond some risky threshold, that while remaining below the threshold for the twin city. The metric being sensitive to each individual indicator can run into the risk of not recognizing some indicators passing a threshold of risk. Okay. There are two possible solutions that we identify in the literature for the problem of average. I think the second one is a bit more promising. Grenier and friends, again, then offer this a posteriori evaluation criterion called balance of 1D departure, saying that departure between target and analog must be more or less the same for each indicator. So you look at the three indicators, they must have roughly the same difference for the metric to be, for the result of the metric to be acceptable. Of course, this rules out cases in which the best analog, the one with the lowest dissimilarity value, have some high difference for one indicator, which is countered by the low difference of the other. Okay, so the idea behind this criterion is that the best analog should be good for all the indicators, not bad for one and good for the others. Okay, so target and source should be comparatively similar in all relevant respects. However, there are some problems with this solution, as pointed out or recognized by Grenier and friends. There's significant variability across the 6 metrics, and also for some candidate analog location, the magnitude of 1D departures for all the indicators might still be large. An alternative solution, which I call solution 2, comes from Allegate and friends. When they tried to construct their metric, they first imposed some acceptability bounds on the indicators. So they say the indicator should not be that difference, each indicator, and then they choose among the available indicators a preferred one, that is the one that ranks the analogues, and the one with the minimal value of this indicator will be the best analog as long as it remains within the acceptability bounds. Okay, and Allegate and friends indicate the mean absolute difference between temperature monthly means as their preferred indicator. Okay, its margin of acceptability is at the should not exceed, the difference should not exceed 1 Kelvin degree. And as for the other indicators, the relative difference of annual mean precipitation, which is relevant for the total water availability, should be less than 50%, whereas the mean relative difference of monthly mean precipitations, which has an impact on the infrastructure and lifestyle of a location, should remain below 30%. Now, there are some, I think it's more promising than the previous solution, but there are some drawbacks here too. Notice that the preferred indicator here, the mean absolute difference, is the one that ranks the acceptable climate candidates. Question, isn't this too weak just to stick to one property when trying to quantify the similarity between source and target? Also, notice that the tolerance margins, 50%, 30%, 1 Kelvin degree, are merely stipulated, okay? Now, that enables one to avoid exceeding some risky threshold, but it also introduces some arbitrariness in the use of the metric. And lastly, it could even happen that under these acceptability bounds, no acceptable analog might be found at all, okay? And that's the case, for instance, for the city of Geneva under the arpège climate model, under projections of the arpège climate model. Authors could now find any acceptable analog for Geneva given these acceptability bounds. Now, enough for the problem of average, even though it is closely related to the fourth and fifth problem, the problem of no causal correlations. Now remember, in the standard schemes, especially the approach by Esse, analogical inferences seem to be more plausible if there's some sort of causal connection between the positive analogies of target and source that are relevant to the additional property to be inferred. Nevertheless, the relevant climatic indicators are generally supposed to be mutually independent. There's no causal correlation between temperature and precipitation. In fact, the more independent they are and the more they should be informative. And the more they could give a sense of the statistical correlations among the target and source. Moreover, remember the temporal asymmetry between the source and the target. Now, we find the target, the future climate of the target, by projecting under forcing levels, whereas the current climate of the source is the result of climate change in the previous decades of centuries. And it's very unlikely that the forcing level that led to the current climate will be the same as the forcing level of future climate change, okay? So there will be a different causal mechanism of climate change in the target and the source. And that these two issues together brings us to the problem of non-causal correlations. The dissimilarity metrics only reveal statistical correlations. And in doing so, they neglect the causal mechanism underlying climate change. Last problem. Well, of course, if we don't have any relevant correlations between target and source, how can a low value of dissimilarity drive plausible inferences about the target starting from the climate analog? In the standard scheme, remember, we ask whether a new property possessed by the target, but the source is also possessed by the target. In the methodology for best climate analogues, that additional property is not explicitly brought about. Okay. And so in particular, then, if the climatic indicators we refer to are just physical, then there will be a great deal of uncertainty concerning how to transfer other type of properties, especially non-physical properties, socio-economic, ecological, even behavioral cultural properties from one city to the other. Okay? And so that is the problem of inferred properties, or what we call the problem of inferred properties. That it is unclear what information one can meaningfully extract from the climate analogues that can be transferred to make inference to the target locations, to make inferences about the future of a city. And now, intuitively, guidance on what properties one should infer comes from the context of applications. In fact, the properties to infer are purpose dependent. And the context of applications where spatial analogues are more useful, we claim, is the context of impact, adaptability, and vulnerability studies of climate change, to which we now turn for the last part of the presentation. Before doing that, any question? If there's something unclear, just don't draw anything on the board. But okay. Okay, so let's move on to the last part, where we look for ways to assuage the problems that affect the methodology of climate analogues, to see in what sense we can have a fruitful application of this methodology. In fact, we can ask, as we did in the title, what, if anything, are climate analogues good for? I mean, these 5 problems seem to be really outstanding ones. Okay. So now, according to the IPCC report, climate analogues are actually good tools for assessing impacts, vulnerability, and adaptation to climate change. As the report writes, they are valuable for validating the extrapolation of impact models by providing information on the response of systems to climatic conditions falling outside the range currently experienced at a study location. So they can serve in particular, and they have served to anticipate the effects of climate change on rural areas, that's for agricultural purposes, or on urban areas in terms of city planning. So here we offer a proposal based on 2 positive recommendations to improve the application of the spatial analog methodologies to IAV studies, especially when it comes to city planning. In fact, notice that stakeholders or decision makers, when they're engaging city planning, try to assess the impacts of climate change always relative to their own local context. So they take into consideration the vulnerabilities of their own cities, and they try to engineer risk-specific adaptation plans. So again, a quotation by Hallegate and friends could be telling: the distance between the projected city and its current analog provides a synthetic indicator for the importance of the adaptation to be operated, and the basis for more in-depth analysis of the risks involving various transition paths toward a fully readapted city. Okay? So looking at a present twin city, we claim, can actually be a resource for urban planners in order to better assess the potential risks that their own city might have to face in the next decades. Okay, but of course, urban planners must find ways to assuage the 5 problems. Okay, so recall the first two problems were non-uniqueness problems of the target and the source. Now, as a matter of fact, climate experts nowadays tend to take a pluralistic perspective, whereby they look at multiple different scenarios as a richness rather than a weakness. Indeed, having uncertainty about the future seems better advised to take into consideration a large array of alternatives instead of just banking on one single scenario about which we do not have any certainty. So the larger the set of possible future scenarios, and the better it is. And so likewise, when it comes to IAV assessment, we need to take into account the views of various stakeholders that might have very disparate interests and beliefs and values. Okay, so in particular, when searching for a twin city, no single city might prove to be the best analog of the target city along different dimensions of risk assessment. Okay, so our recommendation, the first one, is that the underdetermination of the target and the underdetermination of the source, rather than being a problem, might be exploited as a resource to find possible climate analogues. Okay, of course, the candidate sources should be subject to plausibility constraints, but in itself, it's not an issue to have a plurality of options. You just have to check each of them. Okay, so the first recommendation is to take a set of plausible climate analogues, okay, rather than focuses just on what the dissimilarity metric would identify as the best climate analog of your target. Of course, some caveats have to be considered with this first recommendation. So that the target must be projected under multiple scenarios, possibly including the last generation of scenarios, SSPs, that are about socio-economic factors. And then the outcomes must be compared with some suitable dissimilarity metrics. The outcomes of the projection should be compared with the present climate of the sources with a suitable dissimilarity metric. The size of this set should be manageable because, of course, decision makers and stakeholders have temporal and financial limitations. Okay, so they can only consider a small set of these plausible climate analogues depending on their own resources. We saw that the request of the condition of lowest dissimilarity value to find the best analog is not sufficient for plausibility. But still, I think, that a low value of dissimilarity is still a desideratum for good analogs. Okay, not a sufficient condition, but somewhat necessary. Okay, you can consider as a good climate analog a city that under certain reasonable metric is climatically so different than another one, or the reference one, obviously. And finally, once we consider the set of plausible climate analogs according to our metrics, then the set should be further constrained by plausibility conditions that are purpose-driven, and that also include physical, socio-economical, and cultural factors that are over and above the climate indicators that the dissimilarity metric computes. And so let's look at an example to see that. A kind of a recent contribution by Pinzon and others introduced a dissimilarity metric, a very sophisticated one, that takes into consideration precipitations and surface average temperature as the key indicators, and also includes a technique to deal with projection uncertainty. According to this metric, the city which is closest to my wife's home city, Santiago de Chile, will be Cape Town in South Africa, okay? With a given model and under a certain scenario, of course, okay? So here it is, okay? Here's Santiago in Chile, and it turns out to be really close to, really similar to Cape Town down here. However, if Cape Town and Santiago don't share certain socio-economic or cultural similarities, as indeed it is the case, then Cape Town cannot possibly be a good source of information about Santiago. The kind of analogical reasoning that you can enact using Cape Town as an analog is very limited in scope. There are, in fact, other areas here in Australia or even somewhere else in South America that have less than optimal dissimilarity values, but still low ones, that could be more useful sources of information about Santiago because they have some other morphological or socioeconomic or behavioral similarities. Okay, now that underlines the importance of local context. And in fact, if you recall solution 2, I mean, that takes care, considering a set of possible analogs takes care of the 2 non-uniqueness problems. Now we have the other 3. Okay, so remember the solution 2 to the problem of average suggests that one should avoid taking averages over all indicators. But in doing so, one should choose a preferred indicator that rank the acceptable analogues, and that's a sort of drawback. Now, the justification, so of course, the justification for preferring this indicator over the other must be provided, and in the framework of city planning, the justification might actually come from the local context. Okay, so depending on the specific purposes of policy making, one factor over another could be prioritized. Okay, stakeholders might be more concerned about raising temperatures in urban areas when you need to evaluate air conditioning plans. But rather than raising temperature, maybe water scarcity or lack of precipitation could be a more useful preferred indicator in rural areas whose economy depends on agriculture. So this teaches us that target and possible analogues should actually be compared with respect to other local properties that are non-climatic and takes into account also socioeconomic and cultural aspects of the cities. And in these respects, we get to the second and conclusive recommendation. We suggest to integrate local knowledge in the comparison between the target and the potential analog. By local knowledge, we mean a concept that refers to, broadly speaking, various forms of epistemic goods that are produced by human communities when they are in direct interaction with their surroundings, with the environment. And there's a large literature on local knowledge that has also been used in adaptation studies to climate change. So we recommend that the search for plausible climate analogues should integrate local knowledge about physical, socioeconomic, and cultural local properties of the target and the candidate source location. So we should use local knowledge to further restrict the set of possible analogues. Okay. Two examples here. Think about floodings, the example of Venice. Okay. There, the property to infer is flood hazard. Okay. Now, certainly floodings are proportional to the amount of precipitations. The more rain we get, the more likely floodings will be. But their occurrence also depends on other local factors that are relevant to the specific vulnerabilities of a city. Could be natural factors, the geomorphology of the territory, or also anthropogenic factors that depend on the way in which the city was constructed, depends on city development. Another example, which is particularly enlightening for the case, the problem of non-causal correlations, it comes from Skaf and friends. Here, the goal is to infer the future price of energy, goods, and services. And the authors assume that the climatic indicators of heating and cooling degree days correlate with energy demand. The underlying idea is that there is a causal link between how cold it is outside or how hot it is outside and the energy which is needed in order to cooling or heating, respectively, the buildings. Nevertheless, energy demand is also a function of other factors that are socioeconomic, in particular the cost and the availability of energy, but also other elements, the quality of the buildings, the quality of the heating systems, and also the population habits in terms of consumption of energy. Okay, so there are a whole host of other correlations that limit the assumption, the underlying assumption of Skaf and friends. Okay, so these two examples are invitation to think at concrete applications of spatial analogues in order to decide what is the best analog for your city. Okay, to go beyond what a low value of dissimilarity can indicate. And so here's our plausibility criterion. For each possible climate analog in the set that you identified, because of low dissimilarity values of different metrics under different scenarios, under different models, then local knowledge can further refine the one-to-one comparison between the analog, the candidate analog, and the target. And the idea is that if you consider some relevant property that is revealed by local knowledge, different from the key indicators of the climate, then if this property is not shared with the target, then it's an important dissimilarity, and that gives you reason to discard the candidate location as a good spatial analog. If instead the property is shared with the target, then analogical inferences about the target might actually increase the plausibility, obviously depending on the specific purpose at stake. Okay. Notice, and that's another virtue of local knowledge, that it can reveal properties that are robust, namely stable under extended periods of sustained interaction with the environment. And in doing so, it enables one not only to consider physical and socioeconomic properties that you can quantify, temperature in terms of physical properties, but also energy cost, which is quantifiable, but also cultural habits of the local communities that are less amenable, more elusive in terms of quantification. But if local knowledge reveals that they're very stable throughout time, then you can sort of consider them as well-defined properties of the city's population. And so here's our proposal, a scheme that combines the methodology of climate models, climate analogues, and standard analogical reasoning. You first look at the 3 climate indicators. You take you consider you take a dissimilarity metric, so a plurality of them, and you compare target and source. Some indicator, here underlined in red, might even be given a preferred role, depending on whether you fancy that solution or the problem of average. But then once you have your set of the potential or possible climate analogues, you further constrain it by local knowledge, by comparing one-to-one different salient, relevant, possibly robust properties between target and source. And if it turns out that, an additional property K is not shared by them, then you can rule out the source. If instead it is shared by target and source, and the source also possesses an additional property K plus 1, then by analogical inference, you might hope that also the target has that property. And so I don't know how much time I have to...
Yes, you have time. The idea is to conclude for 6, but you have time.
No, because I think we lost some time, and but anyway, so that was the
don't worry, it continues.
We have a toy example here that of Venice. According to the metric, of course, there is this ranking of the potential sources. Now, the best analog of Venice, even if it looks like Venice, is not a good analog. Las Vegas is not a good analog for Venice, a completely different city, no canals, only artificial ones, just to pretend to be in Venice, to give the tourists that kind of experience. But otherwise, it's a highly populated city that doesn't share any other similarities with Venice, so similarities that you can expect Venice to have in 30 years. Suzhou, more similar than Las Vegas to Venice in terms of city structure, but we're talking about a city of 10,000 people, 10 million people, okay? So clearly uncomparable to Venice, which has 200,000 habitants. Valparaiso is a coastal city like Venice, but it's a very, very hilly city. Doesn't have canals. So it doesn't have the same problem of floodings that Venice has, and is likely to have even more in the future. Okay. So even if they have comparable climates, Valparaiso can hardly give good useful information for Venice. Strasbourg, it's much closer as a city to Venice. They're comparable in terms of population size. They're also in terms of maybe cultural habits of the population. Certainly, I mean, Europeans are more similar to each other than other continents. But and also the structure of Strasbourg with all these canals really resemble the structure of Venice. But Strasbourg is already colder than Venice, and if temperature will increase, the climate of the current climate of Strasbourg will be very different from the future climate of Venice. Okay, but so for each, the idea here is that for each of the possible candidates, according to a certain metric, you need to apply local knowledge to further compare target and source. Okay, in order to hope to have, like, you know, some to make some plausible inference about the target. Now, conclusion: as all type of reasoning that are different than deduction, analogical inferences will never give you a conclusion with certainty. So what you can hope at best is to make plausible inferences. Our own plausibility criterion for spatial analogues combines the geometrical approach to dissimilarity metrics that we described at the beginning and the standard one-to-one comparison approach of analogical reasoning. Okay? Here's a saying in English that might be very telling for the case at stake. I might be a twin, but I'm one of a kind. Okay, so it's a warning about inferring too much from the twin city. But something you can infer, even in face of the fine problems that we pointed out. Special climate analogues and twin cities could be good tools for impact, adaptation, and vulnerability studies of climate change, but with some recommendations that we made. First, that you should evaluate a set of possible source locations with low dissimilarity values for the climatic indicators, and then further constrain this set by integrating local knowledge in your analysis so as to find plausible analogues for purpose-driven inferences about the target city. Thank you.